Alright, today's topic is dimensional analysis. Dimensional analysis is really not too much more than a way of checking your formulas in physics. Sometimes we end up having to derive a bunch of like big equations or whatever, and the only way to actually check and see if they're right is to do this dimensional analysis little thing on here. So we're going to go through and I'll kind of show you what it is. Now the only thing that's different, a lot of books would give you like, alright, say for example, if you've got a displacement, which you may not know exactly what that is yet, but displacement's kind of like length. They would tell you to say that use the value of length. I just go ahead and use a unit for length and use a meter. Time, most books would just give you big T and say you're using a time value. I just go ahead and say use a second because that's what you're going to be doing most of the time anyway. I'm trying to sit here and think of like something else, but anyway, you kind of get a little bit of an idea here. So for me, when I'm working these examples, things I'm going to be doing, I'm going to be using like X, I'll be using meters. Velocities, instead of doing length over time, I'll be using meters per second to do my velocities. No idea why I did an arrow here and an equal sign there. Ooh, I could make this big arrow. Wow. Time, I'll be using seconds to work these problems examples. Acceleration, I'll be doing meters per second squared to make these things work. Period, which is the time for one oscillation or for a motion to repeat itself. But again, it's time, so it's going to be seconds. If you see the symbol G for gravity, gravity is an acceleration, which is why it's meters per second squared. Any forces in these problems, I'll be using a Newton, which a Newton is a kilogram meter per second square, if we should use it in any of our problems. I'm trying to think of anything else. Masses, I'll use kilograms. If I see height, I would use meter for it as well, but I think that's going to kind of get us in there. Volume, I use meters cubed. Area would be a meter square. Height would be a meter. I think this kind of gets us off to a decent start here to do these problems. Alright, so the first thing we'll do is I'm going to use this just to check if equations are dimensionally accurate. And I'm going to do example A from the Survey book, but then I'm pretty much just going to jump off on my own and do a bunch of others. Example A says, show that V equals VO plus AT is a dimensionally correct equation. Easy enough to do. All we got to do is substitute in our units. If this equation is dimensionally accurate, whatever unit this side is, this side should cancel to the exact same units. So velocity is a meter per second for a unit, or a length over a time. This stands for velocity initial, which is also a meter per second. Acceleration is a meter per second square. Time is just a second. And if you notice algebraically, that second cancels your square, and you've got meter per second equals meter per second plus meter per second. What that means is meter second, meter second, meter second. That means this is a dimensionally good equation. Everything matches up in there. So let's do a few more examples of stuff with this dimensional analysis. And I might even take a look at some of the problems I ask you to work for homework. So how about this? What about if I gave you X equals 1/2 AT? Is this a dimensionally valid equation for what we have in physics? First of all, the 1/2, we can get rid of it. It's going to have nothing to do with our dimensions in this equation. So I can just go ahead and say X, the unit is a meter. A, the unit is a meter per second square. Time, the unit is a second. If you look, your second cancels your square. And we're left with meter on one side and meter per second on the other, which means this equation is not dimensionally accurate. If this side cancels to a meter, that side's got to be a meter as well. So there apparently is no such equation as x equals 1/2 AT. Now, on the other hand, there is an equation x equals 1/2 AT squared. Because again, the 1/2 we're not going to look at, but this would be a meter equals meter per second squared times time square, which the unit for time square would be a second square. And so now if we look, second square cancels second square, so we've got a meter on the left and a meter on the right, making this one a dimensionally valid equation over here. Now, the other thing is we can also try and use this dimensional analysis to determine what a unit should be. Say, for example, trying to look at some equations I have around me right now. If I was trying to find perhaps what the unit for, well, how about this? What is the unit for buoyancy? B is equal to rho VG. Instead of saying what's the unit for buoyancy, let's try and see if we can figure out what the unit for density would have to be in this equation. And you might already know what the unit for density is, but we'll go ahead and go with it. Buoyancy is a Newton. That's your unit. So I'm looking for density. Volume is a meter cube. And gravity is a meter per second square. Start taking a look. What is a Newton over here? A Newton is a kilogram meter per second square. So now let's take a look. Rho m cubed times m would be m4 per s square. For this equation to work, whatever unit this rho is, that unit would have to cancel this side out to kg ms squared. So kg ms squared equals something times m4 per s squared. So what unit would this have to be to cancel this side out to look like this? First off, there's got to be a kg because this side has a kg. Now, s square, that's good. So what would have to cancel this m4 so that there's only a meter left? Well, if I've got m4 up here, the only thing that would cancel m4 to just an m is m cubed. So m cubed cancels that to just an m over s squared. So we've got kg m s squared equals kg m over s squared. Sorry, I'm losing track of my paper. But anyway, that's a little bit harder one. I'm going to go ahead and work some of your homework problems that you had. Now, I want you to try these on your own, but if you get stuck, we'll take a look at it. Question number 1 just says that show that V equals AH is dimensionally correct. So I'm just going to do that. Is this equation dimensionally correct? Well, what's the unit for V? It's a meter cube. The unit for A is a meter square, and the unit for height is just a meter, which gives you meter cubed equals meter cubed. So this is a dimensionally correct equation. I'm going to skip on to number 2. Number 2 gives you an equation that says x equals bt squared. B is some unknown constant, and it wants you to determine what would be the unit for B. Well, this is a meter. Time is a second square. So what unit could B be? Kind of funny. that would make it cancel out to just a meter? Well, I need a meter and I need the second square to cancel. The only way to make second square cancel would be to have a second square on bottom. If I had second square on bottom, that would make that cancel and you'd have m and m. Now, there's another way of doing this. If you have problems looking at it that way, just solve the equation for b. Do the algebra. X over t squared is what b would be, which means the unit for b would have to be meter over second square. For some people, this would be an easier way of working the problem. Alright. This also has a b part. That was a. You had a b on that question. B says, given the equation, x equals amplitude times sine of 2 pi ft. What is the unit for a, is what it's asking you to find. First of all, sine 2 pi, I don't care about any of that. There's no units. So I've got x equals AFT. What unit would A have to be? So this is meter equals something times frequency's unit is hertz, which is 1 over second, times second. The great thing about this problem is these cancel. So whatever unit A is, it must be a meter, so that you have meter equals meter. Alright. Let's take a look. Number 3. Number 3 gives you this equation. I'm trying to see what it wants you to find. It gives you the equation t is equal to 2 pi square root of L over G. And it just wants you to see if this equation is dimensionally consistent. First of all, the 2 and the pi, I don't care about. So this is going to be seconds equals the square root of meters over meter per second square. Sorry for my little error there. So this would be second equals the square root of meter times second square over meter. Multiply the top by your reciprocal. Your meters cancel. And you've got the square root of s squared. What's the square root of s squared? Second equals second. So obviously this is a good equation at that point. Alright. That's going to be all the examples of work. Do your best on this. And good luck, as always. And once again, so long. Fare thee well, and goodbye. Feel the need to draw something quick. A house. Dun, dun, dun. Oh, it's going to be a beautiful house. Your roof. Try a little fireplace on this end, chimney. Boom. A little smoke rolling out stack. Yeah, it's real nice. Oh, wait, it's bad luck. No front door. Hey, it's a free video. What do you expect?